Okay, so I'm here to talk about extreme heat in Salem. My name is Nicholas Geron. I'm a professor in geography and sustainability at Salem State University. And this is work that was done by graduate students in the geography department in the cartography and GIS master's program. Zaria Fouser, Stephen Durham, and Mikele Pacuku. Pacuku. They worked on different aspects of this program, and this has been synthesized by me and kind of like put into one report. And this is going to be talking about the results of sensors that were placed with SAFE at both at Salem State University. This is the image of the one here on the right, as well as in the Point neighborhood at the North Shore CDC. We'll show that sensor in just a minute. As you can see, this was a family affair. My two daughters were very familiar with the sensor locations by the end of the summer. So for the agenda here, we're going to be going through the introduction, the background around extreme heat, why extreme heat is an issue, and particularly around climate change, but also environmental justice. We'll go over the methods for this study, and then look at the cluster analysis, hourly rate analysis of hot days, so getting specifically on those extreme heat days, and then thinking about cooling, and that's the rate of change analysis. In this class, these are the results. The cluster analysis was the analysis done by Mikele. The hourly analysis was done by Stephen, and the rate of change analysis was done by Zaria. And this is a class that focuses on quantitative methods, specifically statistics, looking at linear and nonlinear relationships, and looking at those relationships over space as well. So, and the image you can see here on the right is a drone image of the Point CDC. This is where the sensor, one of the sensors was, and you can see how the rooftop temperature specifically is around 75 degrees Celsius during one of these extremely hot days. So the temperature that day was over 95 degrees, but the land surface, the surface temperature in this neighborhood, especially on the roofs of buildings, was over 150 degrees. So, which is that 75 degrees Celsius there. So extremely, extremely hot surface temperatures. The surface temperature kind of leads into this idea of the urban heat island. The urban heat island is this concept or theory that urban areas are much hotter than surrounding rural areas. And so the urban heat island describes the difference in temperature between an urban area and a rural area. But urban areas are not homogeneous. They're very heterogeneous. There's lots of variation. And so it's almost more of like a urban heat archipelago with parks and green spaces and large trees providing areas of cooling. But it is driven by land surface. And so as we saw in the previous slide with the drone imagery, if we have surfaces that absorb temperature and re-radiate out temperature and get very, very hot, it can create this very extreme urban heat island effect. And we've seen in the literature that this effect is not equally distributed across cities. So this is an HLC map of Salem from the 1930s, and it's also known as redlining. And so you can see the red polygons are where homeowners were not able to. They were deemed unreliable or undesirable, and so these are often neighborhoods of color or immigrant neighborhoods at the time, and you weren't able to secure a home loan if you lived in those neighborhoods, or really in the yellow ones as well. But it is that's where the term redlining comes from. And we see that places that experience redlining are just hotter nationally overall than places that were in the green or the blue. And you can see here both the national kind of analysis where the red box plot is much higher. You can see the temperature. Whereas, and this is definitely true in the Northeast, which is box plot number C, where you can see that the temperatures are much higher there. And why do we care about temperatures being higher in cities? Why is this an environmental justice issue? we do see that as heat increases, the cooling use and electricity use will go up. So this is research, or a summary of research that looks at how households run ACs, and that this idea of as it gets hotter and hotter, we're going to have more and more cooling days, days where families will need, or households will need, to run air conditioners, and that will, especially in neighborhoods or in the Northeast, like Salem, where our cities are not built for multiple days of extreme heat. So as it gets hotter and hotter, the buildings that we have here are not going to be helpful, and we're going to see increased energy use, electricity use, and that is going to have an impact on household bills and budgets, as we run air conditioners more and more and more, especially during peak demand hours. So these are the hours after you get home from work in the afternoon when it's particularly hot. Those are the times that, we're going to see more inequality in terms of how much energy is needed and how much you have to pay for it. So that really, connects the extreme heat to some of these environmental justice issues. There are many ways to measure, heat, and this is a great image here of all these different types of sensor covers. But the idea is essentially that you want to have consistent, reliable, sensors, and then also the shields around the sensors. The shields are really important to block direct solar radiation as well as block wind. We did look into a variety of different sensor types in order to make sure that the data that we collected would be reliable and not influenced by wind or anything like that. So here's a picture of the sensor that's in the Point CDC. You can see my daughter's looking at it up on the wall. And so it's attached to the building. And just to get a sense of, the temperatures that we're seeing here, again, this was the same day on that extreme heat day. But you can see the sensor, the land surface temperature of the sensor. But that inside of all those kind of like layers of white, they look like paper plates, but inside of there is the sensor. So it's kind of protected both from solar radiation and from wind. So the research questions we were looking to ask is, what are hot days in Salem? Looking at the Point, looking at Salem State's campus. And then we also included a weather station at the Beverly Airport as a control. So what are hot days like? What are the hourly relationships during hot days between temperature, between increases or decrease in temperature, and how these different locations compare? And then how does temperature change, especially during those peak hours? Like, when does the temperature cool? How fast does it cool, especially during extremely hot days? This data was collected from August 8th to September 11th, so we have about a month's worth of data at the end of the summer, but it did encompass a few extremely hot days. So that's what this graph shows. It'll shows the raw data. This is the daily maximum temperature, and then with the three different sensors, and the Point is purple, Salem State is the blue or the teal, and then the red is Beverly. And then you can see the green line is actually the climate average. So that's the 30-year average at this location or at Beverly Airport. The two sensors, we've seen them both now, but the one at Salem State and the one at the Point were both temporarily installed, and the Beverly one is a continuously run sensor where it's collected data hourly. And then we did cluster analysis to determine what are hot days and look at the statistical relationships between them. We looked at, once we had an idea of what the hot days were, we took a sample or looked at the hourly trends across a hot day to see, like, when does it get hot, how long is it hot for in different locations. And then for the rate of change, again, looking at the cooling, that period of cooling after peak energy use or after extreme heat in the afternoon. So for the cluster analysis, this is a classification of basically hot and cool days. And so this was fed into a machine learning algorithm, and it basically identified what days were hot and what days were cool. And then we interpreted those results. The average temperature for a hot day was 30 degrees Celsius, while the average temperature for a cool day was 23 degrees Celsius. The hot days are in the red bars, and the cool days are in the green bars. And what you can see here is that there are many places where SSU, or the Salem State campus sensor, is having a cool day, but the point is actually having a hot day. So good examples of that around August 15th. We can see that Salem State had 2 cool days, whereas in the point that was classified as a hot day. The impact of this means that not only is the point experiencing more hot days, so 10 in this 1 month period, than the point is experiencing 10 more than Salem State University, but the hot days that the point is experiencing are grouped together. And so, for example, that time from like August 11th all the way through to August 17th, we see that the point experienced continuous hot days, whereas Salem State had those 2 cool days to kind of cool off before it got hot again. It's both the length of the heat as well as the frequency of the heat, which is different at these 2 locations. In the hourly analysis, we see that the point sensor as well as SSU are very consistent in terms of their temperature. I mean, the point is a little hotter in the morning, but they're pretty consistent all the way until around noon. It's around noon on this extremely hot day where we see that the point becomes much, much, much hotter. So 4 or 5 degrees hotter than Salem State sensor. And it remains hotter and then cools down slower. You can see like there's the lag in the evening. So it takes much longer for it to get to a cooler temperature. That's an extremely hot day, an example of the hourly analysis. Then if we look at a cooler day, the graph below on the 20th of August, we can see that it's much harder to determine the temperatures on these days. We didn't see as clear examples. The Beverly Airport gets really low. There's a lot of potential impacts, and this could be like a cold front's coming through or different weather systems. So, it's interesting to think about how, the different profiles on these different days, and a reminder of how tricky it can be to model weather. And then along with the hourly analysis, we wanted to create a model to see, what times is Salem State and the point different from Beverly. And so that is what this graph is showing. And we see that Salem State and the point are significantly different from Beverly in the morning, around hour 10 of the day. And that is really because on this extremely hot day on August 11th, you can see that Beverly really dips and is still getting kind of cooler in the morning, while Salem and Salem State University and the point are increasing. And it's a good reminder, too, that the Beverly Airport is surrounded by trees. It's away from Beverly Center, so it's in a really rural location. So you can think of the Beverly signature as a rural signature, whereas the point and Salem are both pretty urban locations, even though, differences in tree canopy cover. There are differences in their profiles, but at least in the morning, they're much more of like an urban signature. So we see the biggest differences between urban and rural in the morning. And then in the afternoon, they're different, but they're not significantly different. We're looking to rerun this model with more data, as well as potentially compare Salem State to the point. So look at like significant differences hourly between the point and Salem State going forward. When we looked at the rate of change analysis. These are graphs that show the temperature decline from the peak, usually around 3 o'clock, or 1500 here, to 8 o'clock or 2000. And the blue line is Salem State, the red line is Beverly, and the green line is the point. And I want to focus your attention on August 12th, which was the hottest day. We can see here that the point and Salem State are both decreasing at a similar rate. So the steepness of the lines is about the same. However, because the point is much hotter than Salem State was at 3 o'clock, it takes longer for it to actually get below 30 degrees. So Salem State gets below the 30-degree threshold, around 4:30. So it's cooled off to below what we would think of as a heat wave. But it takes the point almost until 7:30 for that to happen. And so because of how hot the point got in the afternoon, we do see that there's a 3-hour lag. And so the residents in the point are experiencing extreme heat for much longer into the evening than at Salem State. I'm going to finally talk about these box plots. We did look to see if the rates, so in this case the slopes, were different in any way between the point, Beverly, and Salem State. The p-values are showing you here. They're all quite large. So if there were significant differences, we'd expect to see p-values below 0.05. And so none of these sensors are significantly different from each other. If we look at the first box plot where we have, or the first 3 box plots on the top left, we can see that these box plots are very close to each other. The box plots are showing essentially the distribution of the data at this time, or for each of these locations over the course of all of our data sets. And so there's no real difference in the cooling between Beverly, Salem State, and the point across the month of data that we have. The black line, for example, is the median value, and you can see the median value is usually right in the middle of the box, but the boxes are all kind of matching each other. And so we're not seeing a change in the cooling across our study area. The box plot on the top right looks at sensors on cold days. It does look like Beverly might be cooling a little bit faster. So the lower the box plot is, that's better, right? That's a stronger cooling because these are negative numbers. And then Salem and the point are similar. If we look at medium days, so days that are between 22 degrees and 30 degrees, they all seem about the same as well. But it is interesting to look at the hot days. These are days that are greater than 30 degrees. We see that the point is cooling, or Salem State is cooling the slowest, which is quite interesting. The point is next, and then Beverly is cooling the fastest. There were only a few of these days, which I think is why this did not come through as significant. So I think with more data, with a whole summer's worth of data, we only had about 5 of these extremely hot days. So with a whole summer's worth of data, we might be able to find significant differences there. So in conclusion, I want to say that even though this is a small sample size, we were able to find measurable differences between the point and Salem State, as well as between and Beverly. And so it's really promising for future potential analysis over the whole summer. We do find that the point and Salem State are significantly hotter than Beverly during the morning, but not during the afternoon. We are seeing that there are differences in the number of hot days that the point experiences compared to even Salem State, just down the road. And that the rate of cooling in the afternoon, though, is pretty similar between the two, but because the point is so much hotter, it's staying hotter much longer. So we do need next steps. We need more sensors, a longer series of data, and we could definitely incorporate wind, heat indexes, humidity. So thank you. Big thanks to the team who worked on this and did a lot of the analysis, the students I mentioned as well. And we're trying to, there will be a report and a GitHub site where this data could be available.
Big thanks to Nick Geron for giving his presentation. Now, leading into ours, I just want to say a huge thank you to Tower Gallagher for getting Salem State University certified as a campus arboretum. As Nick just discussed, and as Ryan and I will be discussing, having a lot of green space on campus makes a large difference in the temperature compared to urban environments such as the Point, and how Nick just previously discussed.
So we'd like to thank Professor Nicholas Geron for all of his help in completing this research, and also Salem State University for allowing us to do this research and for providing the tools necessary to do so. So thank you both.
Hello, my name is Mia Amaral, and I am a Salem State University senior, and I am studying geography with a concentration in environmental sustainability.
And hi, my name is Ryan Higgins. I'm a junior cartography and GIS major at Salem State University, and we're here to talk about extreme heat in Salem.
And we made this presentation for our drones applications class. So just to provide some brief background information on why we started doing this project, extreme heat is the most dangerous weather phenomenon annually in terms of human health and heat-related mortality. Annually, an estimated 177 heat-related fatalities occur in the U.S. as of 2024. And the frequency and magnitude of extreme heat waves during the summer months has been exacerbated due to climate change over the last half century. Any sustained temperature above 90 degrees Fahrenheit can be extremely dangerous for high-risk individuals, such as children and elderly populations, who statistically are more vulnerable. Any temperature above 100 degrees Fahrenheit are hazardous for everyone, regardless of age. As a highly urbanized area, Salem is predicted to experience about 16 days of temperature over 96 degrees Fahrenheit within the next 30 years, and this has the potential to increase if compounded by climate change and we do not develop mitigation strategies. So what exactly did we research during this project? We used a drone to create the study area map. Drone imagery from the point in Central Campus was analyzed and compared to recognize potential spatial relationships between the thermal properties of different surface types. These surface types that we studied were things such as pavement, green spaces, the roofs of buildings, and sidewalks. Drone imagery was taken at a fixed location on Central Campus at 50 feet height increments. We started at 100 feet and went up to 400 feet. In which we analyzed each image data to observe temperature differences occurring in regard to particular objects, areas, or surfaces.
Yes, and so the picture you're seeing on the right here is kind of part of our methodology of this project, where each picture is corresponding to a different altitude. So the first picture you see is 50 feet, then 100 feet, and so on. And we kind of put points on each of those pictures to assess the temperature of different surfaces at different increasing heights, kind of just to make sure that the sensor is working correctly and kind of data integrity sort of thing.
So a brief overview of the flight information of both of the flights. So we flew the drone over Central Campus. The imagery that was taken was thermal, and both of these flights occurred on August 12th, and they were flown concurrently, one after the other. The Central Campus flight was only 12 minutes long and was flown at 300 feet, and it captured a total of 179 photographs. The drone flew at 3.4 miles per hour, whereas the point flight also was captured in thermal imagery. It was only 4 minutes long, and this one was flown at the 50 feet increasing height intervals. It only captured a total of one photograph, and we used a total of one non-permanent ground control point. And these are two pictures of our study areas for both.
And so these are the results for Central Campus. So we determined that the lowest values were all associated with healthy vegetation, such as trees and healthy grasses. The locations kind of similar to the mean temperature were on light paved surfaces, such as sidewalks and the white roof, the recently painted white roof of Bertillon building. And unhealthy grass had a similar value to these light-colored paved surfaces. The points with the highest values, on the other hand, were values placed on solid black rooftops, very similar to that which used to be on Bertillon before its repainting. And the second warmest points were all on dark-colored driveways of residential houses. So here you can kind of see pictures of the imagery we used, both in thermal and true color, displaying the points for coolest points, the light-colored pavement points, and the dark pavement points. So 35 to 40 degrees Celsius, 95 to 114 Fahrenheit, and the warmest points 63 to 74 degrees Celsius. You're getting up into the 130 to 140 range of Fahrenheit. And the results for the point. So we had the 4 points with the highest values were all locations on the CDC building rooftop, actually, as well as the shed behind. Dark-colored impervious surfaces, so really good at absorbing solar radiation and retaining that heat. And 3 areas of significant shade and additional points on tree canopy cover constituted locations with the lowest values. The shaded locations were consistently coolest. So the hottest points on the CDC building, you're looking at 78 to 85 degrees Celsius, which you're really getting to 150 to 160 degrees Fahrenheit. and shade and tree canopy cover significantly cooler, 29 to 43 degrees Celsius, so 80s to 100 degrees. And so what kind of conclusions can we draw from this data? Well, the coolest locations at the central campus, and the point being consistently areas of shade or vegetation. It emphasizes the importance of shade and green space as surface heat mitigators, especially during periods of extreme heat that are becoming increasingly common, increasingly frequent, and larger in magnitude, especially in the Northeast and Salem. The hottest spots at both sites being attributed to points on impervious surfaces, though they differ slightly. The building roofs at the point and pavement on central campus. These kind of dark-colored roofs at the point contain roster values between 75 and 85, which is in degrees Celsius, while the light-colored roof of Bertillon building had roster values between 50 and 56, similar to points on patches of unhealthy grass in direct sunlight. Kind of emphasizes how the abundance of impervious surface materials kind of really can exacerbate ambient temperatures and extreme heat during extreme heat events. And the temperature values associated with each point remained unchanged when observed from 100 feet to 400 feet, which is good. That means there's no issues with the sensor, so the data is quite accurate. But there was a small deviation in values of points observed at different altitudes, but this is due to errors in the process of stitching the images together and kind of how they warp and change in the perspective at different altitudes.